Okay, we are going to begin the review lesson and discussion for all of the topics in our Unit 5, Work and Energy. And I've started the discussion reminding you what we're here for. We're here to find truth and beauty in a complicated universe in which there is a lot going on. So consider pushing a kid on a swing. There's nothing special about this situation, but this is an example in which there's a lot going on. Over a period of time, somebody gets on the swing, somebody else might pull the swing back, push it forward. There's all kinds of things happening. The kid is up, then he's moving fast. There's air being pushed around, the chain is squeaking. If this is the dad pushing the swing, his muscles are working. Lots of things are going on. And there's many ways of looking at this situation and finding truth and beauty in it. One way of looking at any physical situation, any process that involves actual things, is to look at it in terms of energy, which is a really abstract quantity which turns out to appear in all kinds of different ways. Let's review how we're going to simplify that complicated universe. First of all, we're going to divide all the material objects into either the system category or the environment. And I'm just making this sound more complicated than it needs to be. But this is no different than you do in your everyday life. What I'm interested in right now is this ice cream sandwich. My teacher's grade book is not greatly of concern to me right now. So if we're breaking down if we're considering this situation of the kid on the swing being pushed, it looks like a very large person indeed being pushed. One way we can begin to, if you were a sculptor, you might walk around your subject and look at it from different perspectives. And you might look at it from down low and from up high and from around this side, and you might look at it early in the morning and you might look at it late in the afternoon. As a scientist, we get a similar benefit from finding different ways to look at the same situation. And you never know what you'll learn from a perspective until you try it out. So pick a system of objects. In a description about pushing the swing, let's include planet Earth, and let's include the kid on the swing. There's no wrong or right choice for what's in the system and what isn't. But it is a choice, and you have to make it before we can talk about any of the stuff that comes next. Sometimes the choice is made for you, sometimes you got to make one. In the sketch, we designate what's in the system with the dotted line. We can also label it in words. Once we divide all the objects in the physical universe into system and environment, we need some way to deal with the fact that time passes and things change. So from the continuous stream of reality, we pick two moments. This is another choice. Two choices. And we pretend that we can separate the continuous stream of reality into discrete moments. So perhaps in one moment The kid has been lifted up the top of the swing. The armless child has been lifted to the top of the swing by his father's tentacles. And in the next moment, kid swinging fast at the bottom of the swing's travel. Now, these are snapshots. It's not a movie. The picture doesn't tell a story. It sort of freezes time. The picture's incredibly useful, but you can't show things like motion with the picture. And you can't show precisely maybe how much higher the kid is in the beginning, in the initial moment, than at the end. So we adopted the convention of labeling these pictures with initial and final moments, and we write whatever quantities we can. We have standard ways of reminding ourselves what's going on here. If the kid's not moving, we might write V0 in the initial state. And if we know he's moving here, we might write V in that direction. You don't have to know everything, but write down everything you can. If you know it's not moving, write it's not moving. If you know it's moving, show what direction. Does the kid have a mass? Well, here we don't know. Now you're thinking ahead to the next topic. Once we have divided objects into system and environment, and made, at least in our mind, a division between initial and final states, we can start to describe this situation more precisely with quantities. A quantity, a physical quantity, is something you can measure. Something in the real world you can measure. A physical quantity has a count. A count of what? Well, count how many units. You might measure a quantity of distance in feet or meters, always meters in here. And you need to say how many units and what unit you're using. A physical quantity may also have a direction. Yes, sir.
Is that word next to quantity?
Something, sorry. So once you can turn it into a number, we can look at characteristics of the number. Something that can happen a quantity might be constant. That means that the total in the initial state is equal to the total after. And the first constant quantity we saw was pocket money. If you don't earn or spend any money, your total money is constant over that period. Not every quantity can be described in this way. Some quantities further can be described as conserved. And I think in everyday language the clearest way to say this is a conserved quantity doesn't appear from nowhere, and does not disappear without trace. Like your pocket money should be. If the amount of money in my wallet has changed, it should be because I earned or spent some. It doesn't multiply by itself, and it shouldn't disappear. You have to be a bank to make it disappear. And the example physical quantity, of course, is mass. Changes form in physical transformations, but the total amount doesn't diminish and doesn't increase. And we saw this with momentum. That was our first conserved quantity. And another way of stating this idea of conservation is that the total before plus the change equals the total after. But wait, what if it's decreasing? That can totally happen. Well, of course now, you know that this change could be positive or negative. So the total can increase or decrease. You can earn or spend money. So this is the big theme going to be with us for the remainder of the year and for the remainder of your life. A more colloquial way of saying the same, of expressing the same idea, there's no such thing as a free lunch. Oh. What is energy? I mean, what? Yep. Energy is the ability to do stuff. That can't answer every question. You can't answer every question. You can't understand everything if you keep this in mind. But you can't do anything if you don't keep this in mind. On our first day of lessons, we saw 3 different kinds of ability to do stuff. When a physical object was lifted higher above the earth, it gained the ability to do stuff. We talked about chalk smashing potential. If there was a piece of chalk on the ground, this block in the initial state would have very little ability to smash it. In the final state, it has the potential. You don't need to do anything to it. All you have to do is let go, and that chalk will be broken.
What's that little half circle for?
Oh, I guess I was trying to draw the surface of the Earth. Thank you for the question. Really, it's just the floor of the lab. But what happened from this initial state to this final state, something, a hand perhaps, added energy to this system. We also saw that an object initially motionless and unable to crush any chalk could acquire the ability to crush lots of chalk through its motion after it was pushed. And we found that with the slingshot, the floppy rubber band on the slingshot couldn't smash any chalk at all, but when it was pulled back, all you had to do was let go, and that chalk would get smashed. So even before we were able to put numbers on any of these things, we were able to see different kinds of interaction, giving the system more ability to do stuff. And the first pattern we saw, an increase in energy. Yep.
Is there someone's lunch on top of the projector?
It's a bag of sand. In the first pattern we saw, when there was a displacement in the same direction as the force exerted by an external object, when the force and the displacement were in the same direction, the energy in the system increased. Stretch this way of the rubber band, force this way of hand on rubber band. And this is the quantity that we can call work. Engrave this in your brain in letters of flame. This is one of those that, just for the sake of internet record, that was Jamie yawning, but he's working very hard. He's paying very close attention.
Sorry.
I know. No, I know you're working hard.
Sorry. A lot of notes.
Right? Whenever you see this work, whenever you hear this word coming out of my mouth or on paper in my class, it means something very specific. An external interaction is increasing or decreasing energy in the system. So it's tough because you can't even talk about work until you pick a system. And how do you know whether it's a right choice before you can put numbers in and analyze it? Well, you don't. It's kind of like many real-world situations. You don't know where to start your problem, but you have to start somewhere. This is why I think this is useful, even if you'll never use physics again. In the previous example, if the external force and using our notation from before, if the direction of the external force is the same as the direction of the displacement of the system object, then work is defined as the positive product of the amount of force and the amount of displacement. Yes, sir.
What's the little pad mean again?
Direction of. And this was our first way of putting a number on a change in energy. Because we know if we can measure a force in newtons, and if we can measure a displacement in meters, we can combine those to produce a quantity that has units of newtons times meters, a force exerted over a distance. And that is how we met the joule. The unit of energy, how much chalk can you smash? Colloquially. And this is the first expression we've been writing this in simplified form like this, leaving out the absolute value signs. That this is not, it's not a formula for work. Well, it is, but don't think about it like that. This is a relationship. Among these three quantities. You could express it otherwise. The external force is equal to the displacement divided by the work done. Or the displacement of the system object is equal to the work over the external force. And we used this in all different ways. Anytime you know two of these quantities, you can determine the third. So it's not a matter of you must remember the force to the formula to calculate work. You remember how these quantities are related. Because like in the real world, you make sense of it based on relationships between things that you understand. So before we leave the topic of work, dust up my markers. Consider the situation when an object outside the system decreases the energy in the system. I know. No, yawning happens when... Stop. Mental activity means less physical activity. Less physical activity means your old leftover amphibian brain circuits get activated. Well, I'm not sure about that. Check with your biology teacher next year. I think it's involved.
Not empowered. Is that why we yawn?
I think that's the consensus.
Really?
And I think hiccups is related to that too. They're pretty sure.
No way.
Based on the first, our ancestors that crawled out of a puddle and had to switch from gills to lungs. In this case,
I did that this morning.
but check with me on that. I'm not certified in teaching hiccups. In this case, the hand outside the system results in less energy after. If there was a piece of chalk here, it's going to get less smashed afterwards. There's a displacement downwards. Now, don't get caught. If we drew a force diagram for this block,
Positive amount of joules.
what's the direction of the external force?
The same direction of the
is it?
It's just
What object is exerting the external force in this situation?
the hand.
Ah, yes, the hand. This is the external object. And here's a partial force diagram for the block. The Earth is pulling it down. If it's moving at a slow, constant velocity, what's the force of the hand on it? Same as, more than, less than the force of the Earth?
And it's not moving? Is the block moving?
Yes, the hand moves the block down without letting it smash any chalk. So the block hasn't changed in speed. It's closer to the Earth. No chalk has been smashed. So energy has come out of that system.
The energy is going.
The
force.
Yes, the force of the hand on the block is up, even though the block is moving down. And it's equal in magnitude to the force of the Earth on the block because the velocity is constant. Forget that.
So, wait.
So here is the, let's point out that pattern again. The displacement is in one direction. The external force is in the opposite direction.
Okay. And that's why it's negative.
And in this case, the hand is doing negative work. We see the same pattern if this cart is zipping along with a certain amount of energy due to its movement, and a hand from outside the system exerts a force to slow it down, so that later it's moving more slowly. We see the same pattern with a displacement of the system object in this direction, while the external force is in the opposite direction. Same deal with the slingshot, or a spring. Let's say if this spring is compressed, there's a ball at rest on top of it. In order to do negative work on this system, that means allowing that spring to expand without throwing the ball or smashing any chalk. Initial state, final state. In what direction did the hand push here? To let that spring come up without smashing any torque. Even though the spring is being displaced upward, the hand pushes down.
It just has less of a force than in the initial state.
Okay? So the external force of the hand is in one direction, while the stretch of the spring is in the other.
Okay, I have a question.
So if the direction of the external force is opposite the direction of the displacement of the system object, then work is negative, which we would define as the negative absolute value of the external force times the displacement of the system object. So again, just cause you can calculate it, you shouldn't always rush straight to calculate it, as the next example will show. Kara.
So your amount of work, like if you were to put that on a bar chart, if it was negative, would be like below?
Yes.
And then that would, okay.
Absolutely. Yeah. And so negative work means the total energy in the system is decreasing.
Okay.
Now, watch out. Calculation is no substitute for thinking, because you can have an external force and you can have a displacement of a system object and yet no work done. An easy example to consider if the system includes a ball and earth separated perhaps by some height y, if the hand slowly and at constant velocity moves the object sideways, now, before you get lost in the calculations, just think. Did moving the ball sideways without changing its speed increase or decrease the energy in the system? No, it didn't.
No.
Okay. It can't fall any farther. So in this case, the displacement of the system object was this way. The external force was this way. And as a result, yep, the work was zero. So this is a pattern we see. If the direction of the external force is perpendicular to the direction of the displacement, then the work is just zero. But more useful than formulas? Or let me say, relationships. Think about the physical meaning. Remember the question with the snail and the acorn? There was a test question where we had a, oh gosh, how do you draw a snail? Hey, look, I drew a snail. That's totally a snail. Woohoo! Hooray for me. Thank you. Yeah, well, you know what it is anyway, right?
You know what it is. It's a snail.
I'm glad this is not video. So we had the snail pushing the acorn. I wonder if I can draw an acorn. Oh, look, I drew an acorn too.
God bless you.
Bless you, Eric.
Okay.
So the question was, what does more work? A snail that pushes an acorn half a centimeter, or a steel beam that holds up a big neon
McDonald's.
sign by the highway? Which does more work? Snail on acorn? Or post on sign? On a test, I'll even give you numbers. Golly, force of post on sign is 30 squigillion newtons. Don't be intimidated by the jargon. Force of snail, 0.001 newtons. Don't be, just because there's numbers there, doesn't mean you have to calculate something. it's clear that the snail is doing more work. Well, the snail is making energy change. This little patch of ground and this bit of acorn, this is warmer now. The snail did something.
Internal.
Yeah. It added energy to some system. System of acorn and earth has more energy than it had before. Whereas this big old signpost, not changing anything. Not adding, not taking away. Good so far? All right. Flavor of energy number 1. So, we've got this idea that the total energy before plus the change, this is what happens over time, equals the total energy after. But we saw different ways that energy could be seen. There was the moving energy. There was the elevated from the earth energy. There was the stretchy energy. And then there was energy inside. Yeah. So the kind of energy that some object has when it's moving is called kinetic energy. And remember, as soon as you have a system object, and as soon as you have picked a moment in time, where you can identify the velocity of this object, you can put a number on the quantity kinetic energy, symbol big K, with the mass of the moving object in kilograms times the velocity of the moving object in meters per second squared and divided by 2.
Is spring constant a lowercase k?
Yes, yes it is. But of course, you don't always need to calculate. If there's an object that's not moving, no kinetic energy. Kinetic energy is 0. What are you going to see if kinetic energy increases? You'll see something moving more. If it decreases, that means something in the system is moving less. The next flavor of energy, gravitational potential energy, is the type of energy you get when you have some object and our beloved planet in your system. If you separate the Earth and that object, they have the potential, they're going to pull on each other and you could smash some chalk as a result. This is what it looks like if you're increasing gravitational potential energy. This is what it looks like if it's decreasing. What's trick number 1? Does this box by itself have the ability to do anything? Okay. Box alone has no, and let's roll out the symbol. U for potential, G for gravitational. The box by itself can't do anything. So we would only say that it is the system of the object and the Earth that together has some UG, some gravitational potential energy. It's not that. Can you choose a system that doesn't contain the Earth? Absolutely. Does that mean if you let go of the box, it's not going to fall? No. It's the same reality. The box and the Earth pulls on each other. The choice of system is how we put numbers to it and account for it. No Earth in system. We can't use gravitational potential energy. So, but if reality is the same, what's your question?
I was going to say, if we want the object to move, we need an external force.
Let's look at the. Let's very quickly analyze these two different choices.
If the Earth wasn't in your system, it would be the external force.
Excellent. Yep. Let's consider what happens if the box is dropped. If the system is box and Earth, initially, box high, not moving. In final state, box low, moving fast. We would say this is an example of gravitational potential energy in the initial state becoming kinetic energy in the final state. If the Earth is not in the system, it's the same reality. Box up here, not moving. Box down here, moving fast. But without the Earth in the system, we'd say that the K we see in the final state comes not from inside the system, but by something outside the system doing work to change the total amount of energy. What's that? The Earth. So whenever you tell me, or you're preparing to tell me that work is done, tell me by what? So red system, blue system, same reality, different way of keeping track of it. Like when I took $5 from my wife's purse. Did I get $5 richer?
No.
Depends how you look at it.
Oh, yeah, I know what you mean.
Okay? It's the same reality, accounted for differently.
Depends if you have like two different salaries.
That's right. Now I can buy lunch. I'm richer. But I can't pay off my mortgage any faster.
$5.
And depending on the circumstances, one way of understanding this may be more appropriate. Same with the choice of system. So, how is it possible for the same circumstances to be interpreted so completely differently? Well, you have parents, right? You're constantly interpreting the same physical circumstances completely differently. Questions so far?
Nope.
Okay, I think we are going to stop for the time being. We've made it from system and environment. No. You're applauding for yourselves. Yes, you are. Because look at this. Look how much you have learned. Can you believe it?
Yeah.
All right, stop the tape. I hope we caught that.